Hello there, actuaries! In this video, you'll learn how to get a perfect score on the first 15 to 20% of exam PA, which is always focused on data exploration. This will be a fun lesson. You'll learn about pretty data visualization in R using ggplot2. The syllabus has a number of different topics all about the same thing. This is analogous to a job description that has a lot of complex vernacular, but then the day-to-day activities are quite simple once you start doing it. So here are the objectives from the syllabus. The first is translate a vague question into one that can be analyzed with statistics and predictive analytics. Consider factors such as available data and technology, significance to business impact, blah, 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 and implementation challenges to define the problem. Understand the key principles of constructing graphs. Create a variety of graphs using ggplot2. Data types and exploration. Identify structured, semi-structured, unstructured data. Identify the types of variables and terminology used in predictive modeling. Understand basic methods of handling missing data. Implement effective data design with respect to time frame, sampling, granularity. Apply univariate and bivariate data exploration techniques. Data issues and resolutions. Yes, as you can see, there's just a lot. This shows you the total relative amount of money in the world. As you can see, not much money is in silver or in cryptocurrency, despite the huge trends right now. Even military spending, which we think is relatively large, is right here. This is half of the U.S. Deficit. If you look at the number of coins and banknotes in circulation, see that the U.S. has the largest, followed by these other powerful countries, Europe, China, Japan. Here's the federal balance sheet. And look at this entire part was just added since January of 2020. Isn't that ridiculous? Here are all of the US billionaires in the world. There's all the money in the world if you had gold, jewelry, or below ground reserves. Here are the Fortune 500 companies. Look at that, just Microsoft and Apple. So if you were to just take like Microsoft, Apple, Amazon, Alphabet, aka Google, and Facebook and put them together, they would have enough to pay off the Fed's balance sheet. Or they would have, if you took all the billionaires in the world, they would be able to buy out Microsoft, Apple, and Amazon. That's interesting. That is why actuaries will always have secure jobs. A picture can sometimes speak 1,000 words. And when you do data visualization, sometimes you need to just look at things from different ways. And there are two methods to this. There's exploration, which uses your left-hand brain, and there's communication, which uses your right brain. Exploration is about speed, iteration, agility, many dimensions, tidy data, which we'll talk about later, and specific tasks that you'll work on for exam PA. Conversely, the communication role is for simplicity, professionalism, consistency. You'll do this on your executive summary. There are different phases, and they're all connected to each other. You begin by taking in the data. This is a CSV file. Then you'll run some queries, transformations. This is also called tidying. Then you'll create some graphs. Usually these will be predefined for you, so you will only need to interpret them. Then you'll fit various statistical models. Sometimes you'll notice things that are not quite as you expect on the model, so you'll go back to the data, make some changes, refresh the data. Then, when you begin to run out of time, you will transition into writing everything down into your report. The transformation phase comprises creating new features, reducing factor levels, applying log transforms, and creating bins for numeric variables. Visualization is when you will create graphs in ggplot2, understand key principles of constructing graphs, create summary tables, and inspect the target variable. Of course, when you model, you'll be first splitting the data into training and testing sets, and then fitting and interpreting models. Finally, when you communicate, you will clearly explain what steps you took and provide professional quality visualizations and tables. So how do you make graphs in R? Quite simply, first you have to take some data, then you will, well, in this example, there's a small sampling that's applied to it to make the graph easier to read. But then you will just call the ggplot function. Gg is for a geometric something, and AES is aesthetic. So in the aesthetic argument, you always put the variable that you want to see in the graph. So once you have this geom object P, you then add to it a graph. Let's add geom histogram, and that's what it shows here. You could also add a geom frequency poly or a geom density. You can also change the color of your graph using an argument like fill equals dark blue. If you want to make a graph of more than one variable, such as a scatter plot with risk score and age, you have to specify multiple variables in the aesthetic. So here x is risk score. See that this is on the x-axis, y is equal to age. Then you add a geom point object. The first type of graph that we'll look at is called a histogram. This shows you the overall distribution of a numeric variable. On the x-axis, you see the range of values, and on the y-axis, the frequency. If the graph is symmetric, then the mean will be equal to the median. That means that it will that if it's a predictor variable, you won't need to apply a log transformation. If this is a target variable, such as y, the response, you could just use an identity link function in a GLM. What's more common is that you see a right skewed variable. This is where the mean would be higher than the median. If this was a predictor variable, you should apply a log transform to make it more symmetric like this. If this was a target variable, then you should use a log link function in the GLM. If the mean is less than the median, like this, meaning that the mean would be down here and the median would be near like the center of mass of the points, then this would be left skewed. This would not be fixed by a log transform. Be careful that you specify the right number of bins. Otherwise, your histogram will have a problem like this, where there are all of these spikes. You can change this by adjusting the bin width in the histogram argument. Histograms are useful for telling whether or not a categorical predictor is predictive of a target. So here, the predictor variable is called x, and this shows you the distribution of the target, y. So imagine that you're predicting automotive crash claims, the amount of claims from an auto policy. And you look at 3 different colors of cars: red cars, green cars, blue cars. And you notice that the crash scores for the crash claims for red cars are much lower than the claims for blue cars on average. That would mean that the variable color is a predictive value in determining the claims. On the other hand, if you looked at the histograms and noticed that these distributions were approximately the same, that would mean that color is not a significant predictor of claims. Now, one caveat to this is that you're not looking at other variables at the same time. That's why just looking at a simple graph isn't enough. You need to put all of the variables together into a model. The next type of graph is the bar plot. This shows a category on the x-axis and the number of records on the y-axis. These combine levels with, so when you look at bar plots, you should combine the levels from groups that don't have a lot of records. Let's say that I was looking at the month of the year. This is January, February, March, April, May. And I noticed that these months here only have a few records. I might combine these all together to form a new group called Other, so that when I fit my models, they will have a significant sample size. Otherwise, the p-values, when I fit a GLM, will be really large, meaning that the data just doesn't have enough credibility. I'd also note that if the values of the target are significantly different between those groups, I shouldn't combine them. In other words, if in May the average claim amount was $1 million, and in June the average claim amount was only $10, I shouldn't combine those two together, even though they both have only a few observations. The third type of graph is the box plot, also called a box and whisker plot. It's called this because there is a box that represents the interquartile range. That's the difference between the 25th percentile and the 75th percentile. The line in the middle of the box is the median, also known as the 50th percentile. Then these whiskers here show you the Q1 minus plus or minus 1.5 times the interquartile range. And then these points along the outside are outliers, or values that are outside of this IQR. They are very, so a box plot shows you the same information that you see from a histogram, except it will also give you specific measurements of the median and so forth. So you should apply a log transform to the variable before creating the plot if you use that log transform in your model. One useful case for box plots is detecting interaction variables. Here's a factor-factor interaction. There's a difference in the median box centers across the categories. So this is a graph that's looking at two variables, morning or night, and stop sign or other. Other could be a yield sign, or just a right turn, or just a left turn, or so forth. If you look at this group here, notice that this red box is lower than the blue box. Compare that to this side, where the red box is, the red center is slightly higher than the green center here. If there was no interaction variable, then they would look like this, where the left box plots are essentially the same as the right box plots. The next type of graph is the scatter plot. The advantages of the scatter plot are that it shows correlation or nonlinear relationships between numeric variables, and they are quite easy to read. Disadvantages are that they get crowded with many observations, because each point on a box plot represents one record. They are skewed when outliers are present. This is what a box plot looks like when you have a lot of records. You can fix that by making the points transparent and smaller. In ggplot2, you do that like this. Scatter plots show you numeric interactions. Let's say that your y-axis was your target variable, your x-axis was a numeric predictor, and the color was a second predictor. So a point can either be green or red. The slope of a line here is the same no matter which color of the point you have. If you had two different slopes, then that would indicate that there's an interaction between color and predictor 2. The next phase of data visualization that we'll talk about is just the importing. This is when you take the data in. For exam PA, there's nothing complicated about reading the physical data, but you do need to comment on the data source and the time that it was collected. You also need to consider regulatory or ethical concerns. If there's anything that should be mentioned, you need to write about it in the report. So here are some examples of data sources. You might look at all patients who have been admitted to a hospital, or traffic accidents, insurance claims, or customer phone calls. Just some concerns that you would have are hospital patients having private information about their race or political affiliation. Traffic accidents that use data from 2015 to predict accidents in 2020. That's too much time between when the data was collected and when it will be used. Insurance claims that use illegal variables in a pricing model, or customer phone calls using data that can't easily be explained. Here's a real example from a major insurance company in the US just a few years ago. One of the largest insurance carriers in the world was accused of racism over their use of a predictive model. They used medical claims to predict health recovery in hospitals. They were predicting health costs, but minorities appeared sicker simply because they had less access to affordable care, and so their claim amounts were higher on average than a white person who had better access to care. So they had to spend more on average. Another example is racism in court sentencing. A federal court used a predictive model to estimate the probability that a criminal would recommit a crime if they were released. They used arrest data, and they were predicting drug offenses. Black people were much more likely to be searched by police than white people, so they had more arrests. Even though the model did not contain a race variable, the results were racist. Tidying covers a broad range of topics. Think about this as your pick and shovel. You have a huge pile of data, and you have to just dig through and find the planted mistakes that the SOA puts in these exams, clean up the data, and then put it into your models. So you'll first read the data dictionary that they give you on the project statement and check that it matches the physical data. Identify the types of variables, check missing values, decide which timeframes and variables you'll use, and set your base factor levels. You'll have to fix missing values. There are 3 types of missing values. The first is missing at random. Remember this, if you spill coffee on your laptop and that deletes your hard drive, that data would be missing at random. Maybe you were working on an actuarial project, some of the data was on your server, some of it was on your laptop, and all of the files from your hard drive suddenly go missing. there wouldn't be a pattern between the values, the missing values, and the actual data. Hidden missingness is when there's just an error in the data. Imagine that someone is typing in a person's name into a database and they misspell that name, and that results in values not being filled in correctly. That would just be an example of hidden missingness. Or another example is you look at your data dictionary from a project statement and notice that one of the values doesn't match what it's supposed to. A final type is missing not at random. Imagine that you wanted to know the percentage of people that used illegal drugs. So you walk out into New York City and you ask 1,000 random people, do you use illegal drugs? Some people say, I don't want to answer that question. That would be a missing value. Now, would there be a pattern between whether or not people decide to ignore you and whether or not they're using drugs? Probably yes. So how can you fix these values? Well, the first is that you could just remove the observations altogether. You should use this only when there are a few missing values or when they are missing at random. You can create a new level called missing and use this when there are more values or when they are MNAR, missing not at random. You can also impute the values with the mean. You should do this when they are numeric and they're MAR. You should remove variables altogether if there are more than 50% of the records missing and there's no way to repair the data. Now that 50% number could be different. It might be 20% of the records are missing, depending on how many variables that you have in the data set and the amount of time that you can work on it. An example, let's figure out which of these variables are missing at random and which of them are not. Our goal is to predict whether or not a person will pass exam P. We're looking at the variables, the hours that they study, whether or not they eat chocolate, if they work in the life industry or not, if they drive to work, or if they bring their own lunch. You look at the percentage of people who pass for non-NA records and compare that to the percentage of pass which have missing values. You notice that 51% of the people who accurately record their study hours end up passing, whereas only 30% of people who don't record their study hours pass. You could conclude that study hours is not missing at random. If you look at eats chocolate, it's 49-49. That's probably random. Life industry, 53%, 52%. That also is probably random. Drives to work, random. Brings own lunch, 55%, 53%. There could be something here. It could be that people who bring their own lunch study while they're on their lunch break as opposed to going out of the office. So you could say that that's not missing at random. So here's a quiz for you. How should you fix each type of missing value? On the left, you see the different types, and on the right, you see the solutions. Connect these dots together for the acceptable ways that you think you should fix them. You can essentially use any method for any type of missingness, except if the value is not missing at random. If it's not missing at random, you should not remove the observations. That would be this connection right here. That's because if there's some info in the data, you don't want to take it away. You want to keep as much info present. Let's talk about feature engineering. Feature engineering is when you create new variables from existing variables. So this table shows you a number of mathematical expressions and their formulas on the right. These are all derived on your predictor variables, the x's. As you can see, there are a lot of different things you could do with your variables to increase the predictive power. You could just take the difference, a log, you can make polynomials, powers, ratios of polynomials, and so forth. The only type of model that will be able to identify these relationships without you manually creating the features are tree-based models, random forests, gradient boosted trees, single decision trees. If you're using a linear model, like a GLM, a lasso, a stepwise regression, then you need to manually create these features. The only exception is the difference here. That's because difference is just a linear transformation, and linear models can pick those up. How do you use tables and summary statistics? You'll have some stats that will be in the template code. You just need to know how to use them. A mean is useful for showing the overall behavior of something. A median tells you what the center behavior is. The max and the min tell you the higher and the lower outliers. The variance or the standard deviation will tell you how spread out the values are. And a percentage is similar to a mean. It just tells you the overall behavior. Here's an example. This is from June 16, 2020. You were looking at 3 different variables: age, gender, and days. On the left, you see everything from RStudio, and on the right, your report in Microsoft Word. You want to look and see that the values here match the data dictionary. I see this goes from 1 to 14, and this says integer 1 to 14. Check. This description is the number of days between admission into and discharge from the hospital. Okay? For gender, I see that this should be either male or female. But in the data, I see that there are 3 values here, which are either unknown or invalid. So these are really NA values. For age, I noticed that this age is supposed to go from 10 up to 100. If I just look at the summary function in R, it just has this big other category. So there could be some missing values in there. So I want to look at the actual counts of these records, and that's what I can do here. And then in the Microsoft Word report, I have to write all of this down. So for gender, I would say there are 3 missing values. I just removed these because there are not enough values to make a difference. And I provide some commentary on the target variable. I say the target variable, which is days, is the number of days the patient has stayed in the hospital after being admitted. This has a mean of 4.4 and a median of 4. Again, I got that from looking at the mean, the median, indicating that it's right skewed, which you can also see from the histogram below. Now let's talk about some more of the right brain behavior. How can you communicate using graphics? How can you create useful graphs? Here is a histogram. This shows you the distribution of readmissions. Now, what are the y-axis units? It just says density. If you showed this to your manager who wasn't an actuary, they might not know what density means. How can you translate this graph into English? Here's a much better equivalent. The y-axis shows you the number of hospitals. In English, you could say there are just over 2,000 hospitals with between 30 and 50 readmissions. This combines the tabular info that you get from a table with the visual power of a graph. In ggplot2, there are some parameters that you'd use to create a graph like this. First, you make the histogram, then you change the axis labels and the formatting of the numeric scales, and you do the same for the x-axis. Graphs should be unambiguous. Here's a mixed bar and line graph. It's trying to show you the actual versus predicted readmission rates. I'm looking at this and I see, okay, blue is average of predicted readmission rate. Orange is average of expected readmission rate. And I'm looking at these different states, Illinois, Massachusetts, North Carolina, etc. When orange is above blue, oh, that's the right axis is predicted, the left axis is actual. Wait, so which is right? Is it the left axis that's orange? Oh, I see. Orange is expected, so that's actual. Wait, expected is predicted. Oh, so expected is orange, which is this right axis. Do you get the point? It's really hard to understand this graph. A better alternative would just be to look at a dot plot. Here you could see that Massachusetts has higher expected than actual, meaning that it's an overestimate. North Carolina has lower expected than actual, which is an underestimate. Pennsylvania has perfect estimate almost. You can also show uncertainty in your graphs. This box plot shows you the spread of values. Notice that Pennsylvania is right about 1.0, which is perfect. However, they also have a wide range of values. Compare that to like North Carolina, which has a narrower band of values, but they're slightly biased high. They're overestimated. Now you can create this exact graph in ggplot2 with these parameters. Now don't worry, I know this is a lot of code. You don't have to remember it, but let me just show you some of the key knobs that you tune if you want to adjust your own graphs. So here it creates the box plot. This outlier alpha adjusts the color of these points here. This coordinate flip is flipping the whole graph 90 degrees. This GG title changes the title here. Of course, Y labs is actually on the x-axis because I flipped the graph. And then these subtitle and captions is this commentary here that goes under the title. You should never have to guess which colors are good. Some people can have a natural instinct to tell which colors look good together. I've never been able to do this, so I've always relied on color wheels. The trick is that you choose colors which are opposite. If you have a graph with 2 variables, just choose 2 colors. If you have 4 variables, then choose 4 colors that are opposite on the color wheels. This is what happens if you don't. Your graphs will not have complementary colors. You can take your colors from your company's website and then create your own themes and color palettes. You can put them into R and create beautiful visualizations like this. How do you be persuasive when you're using data visualization? This comes back to your right brain emotions. First of all, realize that you can't win an argument. If you go into a sales presentation and say, I'm going to convince this client that our actuarial services are the best so that they'll buy. And I'm going to do that by showing them all of these really convincing graphs. If you have that mentality, you will not be successful. Instead, think of yourself as a radiologist, and you're taking some x-rays of the data and you're presenting them to the doctor, and you're not trying to make a diagnosis. You're letting the doctor do that. Show them the data and let the other person arrive at the conclusion themselves. Put yourself in the other person's shoes. Use their language. Think about what they already know and speak from their point of view. Be friendly, of course. Try to smile and use good humor. Get the other person agreeing with you. Get them saying yes, yes. At the beginning of this presentation, I showed you something that you already were familiar with, money, markets, visualizations like that. Start off with something that they already know and they're excited about.